All right, so this is our writing models part 2. We're writing quadratic models part 2. And in these questions, you're going to see that you're not really even given a graph. So you're not given an equation and you're not given a graph. And so we need a way to write a quadratic equation. So what I've got on here, these are all going to be what we call vertical motion, and that's going to be kind of misleading because it's not just vertical motion. This is going to be for when we throw things or hit them or drop them. So these pictures that I've got going on, we've got a golfer who is hitting a ball upward, a volleyball player, that's my favorite, who's hitting a ball down, and then a coin being dropped into a piggy bank. So each of these fit this template equation that's up at the top. And this template equation compares height over time. So that's the h and the t. Notice that this is not x and y, but you can kind of think of it that way. So we've got height and time being compared in this equation. And the numbers that are going to go in front of our t and in front of our t squared and then our constant are all about that first one. The quadratic piece is all about gravity. And that's this acceleration due to gravity. And either we're going to be measuring in standard units, which is feet and seconds, and that's going to be, gravity is always negative 32 when we're measuring that way. And if we're measuring in metric instead of standard, this should be a negative because gravity is always going down. It's always negative 9.8 in metric units. So that's actually the same number all the time. But you will need to know that if we're measuring in standard, you want to make sure you're in feet per second squared, that's negative 32. And in metric, we're negative 9.8. Okay, that's going to go in your quadratic term. Actually, half of that is going to go in. And then that linear term, the middle term, that's about your initial velocity. And in parentheses there, I've got it can be positive, negative, or 0. So let's look at these 3 examples again. In this first example with the golfer, she's hitting the ball up. So her initial velocity, by the way, that little 0 at the bottom, we call that, sometimes you'll hear it called V naught. V naught, and that just means like the beginning, the initial velocity when the ball first is contacted, that V sub 0. So I'll call it that, V naught. And in this one, since she's hitting the ball up, her initial velocity is positive because she's hitting it upward. Whereas in the second example with a volleyball player who's hitting the ball, trying to hit it around the block there, his initial velocity is actually negative because he's trying to hit the ball downward. So he's a negative velocity. And then this last example where we're dropping the penny, we're not throwing it up, we're not pushing it down, we're just letting go. And that means our initial velocity is 0. We're not giving it anything. So that's why I said that the initial velocity can be positive, negative, or 0. So we'll have to be careful about that when we write our equations in these vertical motion problems. And then the constant at the end of our equation is all about the initial height. So for this golfer, that initial height, she's hitting it off the ground, so that initial height would be 0 for them. The volleyball player, when he initially contacts the ball, I don't know, we'd have to estimate. Maybe he's up maybe 10 feet in the air, not really sure. Depending on how high he's jumping, they're pretty far up there. And then for this coin that's being dropped, it looks like maybe its initial height's maybe a foot above where the ground is for that. Okay, so initial height is going to go in as our constant. So let's just go ahead and practice this. So in this example, it says that after the semester is over, you discover that the math department has changed textbooks again, so the bookstore won't buy back your nearly new book. And I know we don't do that here at this school, but you may do that in college where you have to buy a textbook for a class, and then at the end of the semester, you can usually sell that textbook back to get some money back, but not always. Sometimes they don't want the book back. So that's what's happening here. You discover that the math department has changed the textbook and they don't want any books back. So now you're stuck with this book. And of course you don't want it. So it says that you and your friend Herman decide to get creative. You go to the roof of a 12-story building, look over the edge to a reflecting pool 160 feet below. And basically you want to get rid of your book, so you and Herman. It says that you drop your book over the edge, so you just let it go. At the same instant that Herman, who apparently hates his book a little bit more than you, throws it down. He's trying to get rid of it fast. It says he chucks his book straight down at 48 feet per second. So that's his initial velocity. By how many seconds does his book beat yours? So even though gravity is working on both of your books in the same amount, he is giving his book a little bit extra push. So it's going to hit the ground or hit the pool faster than yours. So we're going to need two equations, one for you, one for Herman, right? For you, your initial velocity, you're just dropping it, right? So your initial velocity is going to be 0. For Herman, his initial velocity, he's throwing it down, so I'm going to make this negative. His initial velocity is going to be negative 48. So remember, those are going in as the middle term in our quadratic. Both of you are standing on top of this 12-story building, and it says the reflecting pool is 160 feet below you. So your height is 160 feet above. So is Herman's. You're both standing there together. So you both have the same initial height. And then you also both have the same gravity. Did you notice that our units were in feet? So that means we want our A value, our acceleration, our acceleration due to gravity is going to be our negative 32 feet per second squared. Same for Herman, since we're also measuring his in feet. So if we plug those three values in, that's what it's going to look like for you and for Herman. Half of negative 32 for you, half of negative 32 for him. Your initial velocity is 0, his initial velocity negative 48. Both of your initial heights 160. And then I just went ahead and simplified those. Half of negative 32 is negative 16 for both of you. Since your initial velocity is 0, we don't really need that term. And his, since it was plus a negative 48, I just made that minus. Okay, now what are we going to do with these equations? What are we trying to find again? It says by how many seconds does his book beat yours into the water? So when the books land in the water, their overall height is going to be 0, right? They're going to be basically, it's like they're going to be on the ground, except in the water. So what we need to do is plug in 0 for h in both of these and see when does your book get to 0 feet and when does his book get to 0 feet. So I went ahead and did that. And this is a great problem because we can see our different solving methods. We could do, we could do quadratic formula on both of these. They're both ready. You would know that in your equation, your b value would be 0. And Herman's got all three, A, B, and C. But since it's the notes and I can do it the way I want to, I'm going to avoid quadratic formula if I can. So this first equation, I would definitely avoid it because the variable is only in one place. So we should totally do the square root method, where we just get that variable by itself and then square root. So I went ahead and did that for you. There we go, for you. So I subtracted the 160 over, then I divided by the negative 16. So t squared was 10, and then I square rooted both sides. So I've got plus minus 3.16. But we know that in context, it's not going to take your book negative 3.16 seconds. So really, we know that your time, we only want the positive there. It takes your book 3 seconds, a little over 3 seconds, to fall the 12 stories. Okay, so let's see how long Herman's takes. And again, since I want to try and avoid using quadratic formula just because I can, I'm going to see if this is factorable. But those numbers are huge, so I want to make them smaller. So I'm going to divide everything. 16 goes into everything. But we talked about on a different video that it's really hard to factor if that first term is negative. So I'm actually going to choose to divide both sides by negative 16. That way that first term will be positive. So 0 divided by negative 16 is still 0. Negative 16 divided by negative 16 is 1. Negative 48 divided by negative 16 is 3, and positive 160 divided by negative 16 is negative 10. And this is a super easy one to factor. Our quadratic piece is t squared. That can only come from t and t. Our constant piece is 10. That can only come from 1 and 10 and 2 and 5. Since that 10 is negative, this is a difference table, and we need a difference of 3. Perfect. 2 and 5 gives us a difference of 3 as long as 5 is positive and 2 is negative. Okay, and then we need to solve that. We just need to ask ourselves, what makes this first quantity 0? And then separately, what makes this second quantity 0? Because we have two things that multiply to be 0, so one of them has to be 0. So what makes this quantity 0? Well, if t was negative 5, that would be 0. What makes that one? If t was positive 2, right? So if t is negative 5 and if t is 2. Now we know that in context, time is not really going to be negative. So Herman, remember Herman threw his book downward. His book only takes 2 seconds to get to the water. Yours takes 3.16 seconds. So your book takes 1.16 seconds longer to hit the reflecting pool. Okay, so again, these are vertical motion problems where we're not given a picture and we're not given an equation, but we have enough information to write an equation using our vertical motion template, okay?